So till now we have covered carbocation. We have seen every aspect of carbocation, whatever their stability order, whatever their comparison, whatever reactions involved, carbocation intermediate and the rearrangements also. Now it's time for carboanion and to discuss their special cases. Carboanion is very much similar with carbocation. We know carboanion means carbon having anion, that means negatively charged. So this is basically carboanion, and it will have three different group A, B, C. So one group, for example, it was D. So if this is undergoing heterolytic cleavage with carbon negatively charged and D with positively charged, thus carboanion is getting formed. Now, which factors will stabilize the carbocation? We know if these A, B, C, or all the groups, they are electron withdrawing group. So all the effects, those withdraw electron from this carbon will stabilize the carbanion. So carbanion for simple C minus, we can have a carbanion. We will be calling it sp3 carbanion. So normally carbanion will have hybridization sp3, but it is not always necessary. If C double bond C here negatively charged, that means vinylic anion. So this negatively charged, this carbon will have hybridization of sp2. So in general, carbanion will having hybridization sp3. So we have seen for carbocation, it is sp2, right? But for carbanion, it can be sp3, it can be sp2, or it can be sp also. Now, if we want to compare the stability of these three carbanion, we will see that the stability increases when the S character increases from left to right. Here percent S character is sp3, so S character is 25%, and here S character is 1 upon 3, so that means 33%, and here 50%. So more the S character, we know electronegativity, electronegativity increases. So electronegativity increases means that this negative charge will be more stable on more electronegative carbon. So this carbon is more electronegative than this one. So this system will be more stable. So stability order will be like this. And with this stability order, you can compare acidity also, right? For example, methane or ethane, you can say. Now, if we put number of carbons same, then C2H6 will be lesser acidic than C2H4, will be lesser acidic than C2H2. Acetylene will be most acidic because these are basically conjugate base of these systems, right? So we have seen some basic things about carbanion. Let's go for difficult problems or typical examples. So your a task is to first write the question, pause the video, try to solve yourself, then play the video and match with your answer, learn the concept. So let's get started. First question is compare acidity. So you have to compare acidity. Now questions are CHCl3, CHF3, chloroform, bromoform, CHBr3, then CHCN3, cyanoform, CN3, cyanoform. So we have to compare acidity. Second question, first you try this. Let me first explain this. Okay. So now I am going to give you answer. First try yourself. So here order will be, if we put A, B, C, D, then order will be D, A, B, C. So these are typical problem, very basic questions about these things you know, and these are very easy. So I am trying to make you familiar with these typical problems where you can be confused. Okay, so how to explain this thing? How to explain this order? First, first let's draw the conjugate basis of these three. First one, it will have CN whole three. I am not writing the three, I am writing just one group. Okay, C will be negative. In conjugate base, C will be negative, and there will be three CN. So I am writing just one CN because in all the cases there are three groups. Then CBr minus, then CF minus, then CCl minus. Now here the negative charge, you know, cyanide is very strong, minus R group, so it can withdraw electron with very high conjugation. So that's why D is most stable. So this conjugate base is most stable. So D is highest acidic. Okay. Now these three. Now the fact is this negative charge can undergo back bonding. That is, I would not say back bonding, but a bonding of 2p pi to 3d, vacant 3d. But here 2p to 4d, right? So back donation will give, or donation will give stability of this system. So this system stability and this system stability will be generated due to this back bonding type of phenomena. But here will be no back bonding because it has no such vacant orbital. So it will have no back bonding effect. So even if fluorine is most electronegative, but electronegativity, that means inductive effect. So inductive effect is least prominent, you know. So carbon fluorine, this system, sorry, okay. So electronegativity is this. This system is least prominent. Electronegativity least prominent. Okay. Now here 2p pi and 3d pi. We know 2p pi is like this, and 3d pi will be, for example, like this. Okay, vacant, and it is filled. So this is basically sigma bond. And if we want to draw the pi bond that is going to generate, that is basically this 2p pi and 3d pi. Okay. So here in these three examples, here 2p pi, 3d pi, back bonding. If I write it at back bonding, it is also back bonding. Now, if you have studied back bonding concept in S block chemistry, or you have specifically read back bonding from any sources, then you know that 2-3 back bonding is good, but 2-4 is very, 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 very bad. So almost there is no back bonding. Okay. So in a previous year question, I have also seen that they consider there is no back bonding. So here back bonding will be absent. It will have back bonding. Here back bonding will be absent. Now for the back bonding A, it will be most stable. Will be most stable. Now here also no back bonding. Here also no back bonding. So carbon fluorine, because back bonding is not there. So now the only effect remains is electronegativity. So here electronegativity is higher, electronegativity is lower. Okay, so that's why B greater than C. This is the first example. Okay, let's go for the second one. Let's go for the second question. Okay, now compare stability. Question is compare stability. C, phenyl, phenyl, hydrogen, negative. This is A. Second one, C, phenyl, 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 B. This is negative. Next, double bond O, negative. That is C. Fourth one is allylic anion. That is D. So it's your turn to solve this. The answer will be C greater than A greater than B greater than D. Now, if we compare first two things, A and B, we know in B, what happens? There are three phenyl rings. If this negative charge try to resonance with this phenyl ring, then the phenyl ring should be, this negative charge should be parallel to this pi cloud, right? For the complete resonance. But due to these two phenyl ring, this the steadiness of this two phenyl ring will not let the ring to be in accordance with the uh, parallel parallel p orbital orientation, right? So that's why among A and B, A will be more stable than B, because here actually these three phenyl ring will never be in plane, and two phenyl ring will make static hindrance, and third phenyl ring will be out of plane, and the negative charge will not able to undergo resonance. So that's why overall resonance activity is very much less for B. So A greater than B. Now C and D. D will be least because in these things in A, B, and C there are much more resonance than D, right? So D will be least. So here resonance is very, very low, but in these cases resonance is very high. And this compound, this is special, this is called active methylene compound, active methylene anion. Active methylene means this carbon is actually a methylene carbon. So this type of methylene carbon, where in both the direction there are two very strong electron withdrawing group, this system increase the acidity of this position very much. So these are active in the sense these are very much active toward base. That means this system is very much acidic. Very much acidic means the conjugate base is very much stable. So that's why C will be most stable, and it will be more stable than A and B itself. So the order is C, A, B, T. Now, third question. Now it is a very famous question. Phenyl, 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 negative. Phenyl, phenyl, hydrogen, negative. Now learn the concept before doing that. That to complete a resonance, the pi electron configuration, the pi orbital, p orbital or pi orbital orientation should be parallel to the orbital from which the carbon is donating the electron. So this should be parallel. If there is any distortion, then the resonance will be not effective. So stabilization will not be effective. So planarity is very much essential for resonance of carbon through the benzene ring. So keeping in mind, try to solve this. There is also 3-phenyl ring and the negative charge is here. Fourth example is so these are basically our compounds A, B, C, D. So here, so let me tell you the answer. And the concept here is locking concept. This rigid system here, I have bounded this phenyl ring. Here also 3-phenyl ring, here also 3-phenyl ring. In the first example, here also 3-phenyl ring, but here I have locked the system, right? So due to the locking, the negative charge is now locked. It is in proper plane. The whole system is in proper plane. So there will be complete resonance. So in that, in B, in the previous example, the 3-phenyl rings are there was single bond. That's why they are rotating freely. That's why at a time the 3-phenyl rings can't be planar. So that's why resonance has dropped very much. But here I have tied or locked the whole system. So much resonance will be happen and the complete resonance in the whole ring. So D will be most stable. Then see here locking is less. Here in both side I have locked. Here if I would lock this side, then it will be properly locked. But it is locked but less locked. So DC and AB is the previous example. Uh, B will be higher than A, isn't it? So triphenyl will be less stable than diphenyl. So these are some typical examples. Now let's move some more difficult or more tricky problems. So let's get started. Question. Negatively charged cyclopentyl anion. Negatively charged. Then tadbutyl anion. Tadbutyl anion. Then cyclopropenyl anion. So you have 4. Let's compare the stability. So do this. The answer will be B, A, C, D. A, B, C, D. Why? Because B will be more stable. Why? Because it is aromatic. And D will be least stable because it is anti-aromatic. And A and C, you know, A and C, A will be more stable, C will be less stable. We know the stability order 1 degree, 2 degree, 3 degree, it is the opposite order of carbocation, right? 1 degree greater than 2 degree greater than 3 degree. Why is it so? Because this 3-methyl group will push electron from this side, and this pushing of electron will generate the negative charge, more negative. Okay, negative charge will be more, so it will be least stable. Okay, so among A and C, if we compare, then C will be lesser, A will be more. It was a easy question, right? Next question. Negatively charged. Negatively charged here. Then also cyclopentadienyl anion. This is in short form, it is called CP, just CP. So the order will be A, B, C, D. The order will be C, A, B, D. C is most stable because aromatic, right? C is aromatic. And A and B, what happens? A has extended conjugation, but B has cross conjugation. Sometimes it is in this direction, sometimes it is in this direction. So A will be more stable than B because A has extended conjugation, B has cross conjugation, and D is normal 3 degree anion. Okay, normal 3 degree anion. So that's why the stability order is thus explained. Now, next question. This was also easy. I hope you have marked it correctly. Now compare acidity. You have to compare acidity. HA, HB. Okay. Now compare the acidity with the same concept, cross conjugation, extended conjugation. Which HA or HB, which one will be more acidic? HA will be more acidic because HA negative. Sorry. Here HA. Okay. Because negative charge will be generated here and it will undergo extended conjugation. And here also it is not extended, it is cross conjugation if you deprotonate it. Now the final example of our discussion, and it will be end of Carbanion. It is not much required to study a lot. And those reactions where Carbanion is involved. Some examples, sometimes it is asked in exam that which of the following examples Carbanion will be formed as an intermediate. So you can predict that if any acidic species is there or any acidic species is there, so carbon negative, wherever carbon negative is very much stable, and for example CH was there, then OH minus will attack, then in this system always carbanion will be generated. So this is very much easy to predict for carbanion where actually this intermediate will form. So let's go for our final example. Double bond O, negatively charged. C double bond C, negatively charged. C double bond O, negatively charged. And double bond O, this is negatively charged. Now A, B, C, D. Now it's your turn. The answer will be A, B, D, C. In A, there is resonance. Yes, there is resonance. The negative charge will undergo resonance. Here, resonance. Yes. Here, resonance will not occur because it is bridgehead position. Negative charge, if undergo resonance, then it will be double bond in bridgehead position. That is, according to Bredt rule, BREDT, Bredt's rule, bridgehead position cannot attain sp2 carbon or double bond or carbocation. So there will be no resonance. So, and here will be resonance. So C is the least. Now A, B, and D. In A, it is extended conjugation, isn't it? In B, it is not extended but a conjugation, and here it is cross conjugation. So A have extended conjugation, B has conjugation, D has cross conjugation. And another thing, B and D, B. Okay, no, it is the example. Okay, I was trying to give another explanation, but yes, it's okay. Extended conjugation, conjugation, cross conjugation. So this will be the order. So these are few typical problems I have found. Actually, I used to solve a lot of problems with these kind of systems. And till now, whatever problems I have found a little bit difficult, I have noted them down in my notebook. So these are typical problems, and I noted them because I thought I should revise this before any examination. So these are basically difficult problems which I thought to be difficult while practicing the questions. And these are the questions from Carbanion, which I found to be a little tricky. So we should take care of this example especially. So that's all for Carbanion. In next session, we'll be starting any other reactive intermediates. And carbanion, among all the intermediates, carbanion will be covered in least time because it is not very much very much extensive. Carbocation is very much extensive. In fact, carbene, nitrene, these are very much extensive because too much name reactions are associated with this. So we will be discussing them one by one in the later discussions. So till now, I hope you have understood it. So okay, thank you.